Okay, so thank you. First, I'd like to correct some mistakes. Here, the representative should be of the following form, but the stabilizer and the unipotent radicals are still the same. Here, the representative in each orbit are the following form: gamma times IM000. It's right. I define it to be right action. Representative here is the left multiplication. Yeah. And again, the stabilizer is a parabolic of the. It's not a parabolic, but it's of the following form, and they have the unipotent radical. Okay. Then the zeta integral for each orbit can be written of the following form. So for each orbit, with representative the integration, first the rational summation can be written as, let me just write down the whole integration anyway. G belong to the bracket G, and H belong to G1 bar over GF. And here, you can write the original summation as C runs over PMF and the quotient GF. And here is F of H inverse gamma IM00. And here is the CG. And here's beta 1G and beta 2H. Okay. Then again, we use the fact that the function beta 1 here is automorphic. Then we can absorb, we can do some unfolding procedure for these two variables. And we can simplify the integration to be of the following form. G lies in PM, F, and here's GAF, and H lies in GF, G1 bar. And here is F of H inverse for each representative in the orbit, and here is just G. In particular, we find that when we are doing the integration for the variable g, we can decompose it to two parts. So we write the following quotient to be the product of these two parts. So first part is the unipotent radical part. And the second part is just the other part. And moreover, here we notice that the right action of the whole unipotent radical on the element here is invariant. In other words, for any n belong to UMA, you find that the right action of n on this element is equal to itself. Okay, so in particular, we can extract the integration here. So let's write G as n times, let me see what variable I choose. Oh, it's PM. Yeah, it's PM. Thank you. Yeah. Then we can write the original zeta integral of the following form. F points, of course. Yes, you're right. Then the integration can be written as follows. So you first run G lies in PM F UM A, and here's GAF. And you run over H lies in the G1 bar over GF. And here you have the original function f of H inverse gamma IM00 G. And for the cusp form beta 1 here, you get additional integration. It's U bracket of beta 1 and G dn. Here's beta 2 H bar, determinant of G. Is plus and minus 1 over 2 dg dh. Okay. Then, since we know that beta 1 is a cusp form, so in particular, here's UN. The following integration vanishes. Therefore, the whole integration here is equal to 0. So this is a term for the rank bigger than 0 case. For rank equals 0 case, we use the fact that the cusp form are always orthogonal to a constant function. So for m equals 0, then you get here's F0, and here you get beta 1 G beta 2 H bar dg dh, and here's determinant. Then you simply do the integration in variable h, take integration. And they use the fact that the cusp form are orthogonal to constant functions. Therefore, in particular, this term is also 0. Therefore, we have shown that the boundary terms are 0 in the original zeta integral. Okay. So roughly, this is the global theory of the standard L function of GLN. So any questions? Split. Yeah, as you. Yeah, you're absolutely right. If you want to prove the entire continuation of the zeta integral. I mean, here, this part, I simply take the integration in h variable. Yeah, h variable, this is of finite volume. Yeah. So when you take the, yeah, I know if you, yeah, I know that if you want to run the original procedure, then you need to break the integration here in terms of G1 over GF, then times 0 to infinity part, then it breaks to 2 parts. So any other questions? Okay. Then we are ready to talk about the Braverman-Kazhdan proposal. Okay, so let's fix some notations. We fix our group G to be a connected reductive algebraic group over a local field F. And for convenience, we assume F to be a PID field. There are parallel proposals for the local function field and the Archimedean local field, but for convenience, we restrict ourselves to the PID field case. Okay. Then let's first briefly recall the factorial lifting conjecture of Leyland. And here, for convenience, we assume our group to be split. And then we can fix the split maximal torus of G. Then we know that such pairs are always determined by the root datum. You have the character group of T, and then you have the roots, and then you have the co-characters, and then you have the co-roots. And if you pass to the dual side, then you get the dual group of G. You get G check over C. Okay. Then we can define the Leyland's dual group of G. We let LG to be the Leyland's dual group of G, which is, since we assume our group G to be split, so it's just G check cross the Y group of F, or sometimes the Gallo group of F. And when we are talking about the factoriality conjecture, usually we ignore the Y group part. Okay. We group part, yes, you're right. Yeah, I'm sorry. Yeah. Okay, then let's fix a finite dimensional representation of LG, which we call it to be rho of dimension n. Okay. Then we fix irreducible smooth admissible representation of G. Then a natural question in the Leyland's program is how can we define the local L factors? So question, for instance, how can we define the local factors like LS pi rho? If the local Leyland's correspondence is known for G, like the GLN case, which is due to the work of Hertz-Taylor and Schulze, then we can use the RTL function to define the L function. So if the local Leyland's correspondence is known for G, then we can define the L factor by Lipton. to GL. And then you can use either the Artin function or the L function of Golden manager K. Okay. But usually the question is, if you define the local L factors in this way, then usually it's not useful for global purpose. Like if you want to prove the meromorphic continuation and the functional equation of the L function, then usually you need to use the techniques of harmonic analysis. So in particular, like the examples that we have already seen, you have the GL1 series due to Tate, and GLN, the work of Golden manager K. And also you have the Rankin-Selberg method. And of course, the Lanza-Shahidi as well. So we will mainly focus on the integral representation of L functions. And the Rankin-Selberg series gives you the analytical properties of L function for some special G and some special rho, but it cannot treat all the cases uniformly. Okay. Then what about a general procedure following the work of Golden manager K uniformly for all G and rho? So around 2000, Braverman and Kazhdan proposed a uniform way to obtain the integral representation series for L functions for general G and rho, following the method of Golden manager K. And as we have already seen in the work of Golden manager K, there are two main ingredients in the local series. One is the Schwarz space, and the other is the Fourier transform. Okay. We denote the Schwarz space to be S rho G, and let the Fourier transform to be F rho for notational convenience. Okay. Then in the following, we are going to fix more notations. We need to put some constraints on our group G. We further assume that our group G fits into the following short exact sequence. 1 to G naught to G, and here you have a capital sigma to Gm. Here, let me briefly mention that we assume that G naught is a split semi-simple, simply connected algebraic group over F. And the character sigma here plays a role of determinant. Like the GLN case. Okay. And in order to exclude some trivial case, like if you assume the representation rho to be a trivial representation, then essentially it follows from the work of Tate again. So let's assume that our representation rho is actually faithful. Moreover, we have the following commutative diagrams. Here's rho. Here, the first row follows from dualizing the short exact sequence here. And the rho bar is the projective representation associated to rho. And by the commutativity of the first diagram, you can show that the restriction of rho to the central torus, GM, is given by the scalar multiplication. Okay. So any questions? You may feel that we put some strong constraints on the pair G rho here, but let me briefly make a remark. If we start with the split semi-simple simply connected algebraic group G0, and if we fix a projective representation, rho bar of G0 check, then one can show that then there always exists some short exact sequence in an assumption giving rise to assumptions anyway. But the group G here might be vary. Actually, it follows from the Weinberg theory of reductive monoid. And I think it was first pointed out by Ngo in the study of the Braverman-Kazhdan proposal. So, in particular, if we let our group G0 example, if we let G0 to be SL2, and we let rho bar to be symmetric nth power of PGL2, then if n is equal to 2k, then G is equal to SL2 cross GM. If n is equal to 2k plus 1, then G is equal to GL2. Yeah, so it's not very far away from the original group, but the group might change a little bit. Okay, so any questions? PGL2 G of G0 check. So any other questions? Okay, then let's talk about the conjecture. Then conjecturally, there exists some Schur space, which we call S rho G, lies in the space of smooth functions of G, such that if you run the procedure like the Goldman-Jacquet case, you form the following zeta integral. Then it has parallel properties as the Goldman-Jacquet case. For instance, you have the absolute convergence when the real part is sufficiently large, and then you have the meromorphic continuation and the GCD property, and you have the functional equation. And moreover, you have a Fourier transform acting on the Schur space, gives you exactly the functional equation that you want. Then here, you may wonder what is the parameter L here. Let me briefly mention. Small remark. The complex parameter L, for analytical purpose, is not very important. Since different normalization just gives you unverified shift of your Schur space and the Fourier transform. But for geometrical reason, it's important. It was first pointed out in the work of Bezier and Ngo and Saclarides that the parameter L here should be of the following form. It should be 2 times rho b, the pairing between rho b and lambda. Then what is rho b here? Rho b is a half sum of positive roots. With respect to some Breuer pair, Bt. And the lambda is the corresponding highest weight of rho. Yeah, we assume rho is irreducible. Okay. In particular, let's say in the GLN standard case, then rho b is just n minus 1 over 2 and n minus 3 over 2, blah, blah, blah. And the highest weight of standard representation is just 1, 0, 0, 0. Then if you take the pairing, you immediately get the number n minus 1. Yeah, L is equal to n minus 1. This is what you have seen in the work of Goldman and Jacquet. So any questions? Then let's try to explain more details. I mean, some basic structures for the Schur space and the Fourier transform. Say it again. As I just mentioned, it's work of Bezier and Ngo and Saclarides. Yeah. So first, let's explain some basic structures for the Schwarz space. We have the following three descriptions. So first is the analytical description. The analytical description is just a GCD property that we have just mentioned. In other words, the zeta integral, if you plug in the Schwarz function to the zeta integral, and here phi is a matrix coefficient, then the zeta integral is absolutely convergent for real parts sufficiently large. And it is a rational function in Q to the minus S. Which admits a common generator. Common denominator, I mean. Given by the L factor that you want. Okay. On the other hand, the Schwarz space should also be a Heck algebra module. The second property is that the Schwarz space S rho G should be a HG cross HG module. By left and the right convolution. Okay. And the third property, I think it's one of the most important properties, the geometric property. In order to talk about the geometric property, then we need to recall the concept of reductive monoid, as we have already mentioned in Lei's talk. Then it's closely related to the Wingberg theory of reductive monoid. As we have already seen in the standard case, I mean, when group G is GLN and the rho is standard representation, then we know that G embeds into Mn equivalently. They mentioned the structure of reductive monoid in their 2000 paper in section 5.5, if I remember correctly. Yeah. They do not explain explicit geometric description there, I think. Yeah. This is a G cross G affine spherical embedding, as we just mentioned. And we noticed that the image is open dense, and yeah, let me write right here. It's open dense, and we use some nice functions on Mn to be our space of test functions. So any questions? Yeah, it's fine. Yeah, if you want it to be definition, yeah. Definition as well, yeah. You mean in the standard case? in the standard case, if you, I mean, this is essentially the theorem of Braverman-Kazhdan-Ngo, right? It's a very good question. Actually, I think it's not known right now. Yeah. So any other questions? A question? Yeah, it's a conjecture. Yes, exactly. Yeah. Yeah, it's a conjecture. Buffer essentially use this one. Yeah, essentially use this one. You just use the matrix Pavlovian theorem, then do inversion back. Braverman-Kazhdan-Ngo case, if you want to show that it's exactly the space, I see no one write down proof. Yeah. Yeah, it's something related to the matrix Pavlovian theorem, kind of. Yeah, but no one write down a detailed proof, I see. So any other questions? Okay, then let's continue. Then what about the general pair G and rho? Then with our assumptions before, it turns out that for any G and rho, there also exists some G cross G equivalent embedding from G to something called reductive monoid, which we denote by M rho. This is also a G cross G affine spherical embedding. With open density image. Okay. Here M rho is a reductive monoid. Okay. And here, as Lei just mentioned, that M rho, in almost all cases, M rho is a singular variety. Except the standard case. Up to finite many copies, of course. So it turns out that if you want to run the Braverman-Kazhdan-Ngo procedure for locally constant comparatively supported functions on M rho, then it does not give you the desired property. Yeah, it's not true. A basic example is the GSP4 case. I think it appears in the original paper of Sataki anyway. That to say, if you use the our group G to be GSP4 and the rho is a standard representation of the dual group of GSP4, which is GSP4C. Then oh yeah, it's an accident. It's not general. Yeah, you're absolutely. Yeah, it's an accident. Yeah, let me write here. Yeah, anyway, yeah. Then if you run the Braverman-Kazhdan-Ngo procedure for, let me mention reductive monoid in this case. Then the monoid in this case is the MSP4. Yeah, this is a singular cone. Then if you use the locally constant comparatively supported functions on MSP4 and run the Braverman-Kazhdan-Ngo procedure for zonal spherical functions, then you cannot get the standard L factor you want. Yeah, it turns out that the function should be more singular in the sense that it should be modular growth near the singularity rather than just being constant. Finally, let's give an overview of the geometric description of the Schwarz space. So any questions? Let me briefly, I mean, in the GSP for, how you define the group GSP for? I mean, then is TG J4, I think in this case, G is equal to lambda times J4 for some lambda. Here you need to assume that the parameter lambda here to be invertible. Then what about MSP4? Then you just assume the lambda can be 0 anyway. This is the definition. Does that make sense? Oh. Extra what? Probably you need to assume something like it's an identity component, something like that, I think. It's probably likely, yeah. MSP4, you just need to you just assume the parameter lambda can be 0. Yeah, that doesn't need to be invertible exactly. Yeah. Then overall, we expect that our Schwarz space S rho G should be the competitive supported sections of some Schwarz strip on the reductive monoid. This S rho theta is something like called the Schwarz strip. And here the topology that we use is the p-adic topology. Okay. In other words, as we can imagine that the functions in the Schwarz space should be described by their asymptotic behavior near the singularities. Then let me briefly mention some work of Zhilin Luo and Yanis. They really relate the Schwarz space with the geometry, some element in the Schwarz space, I mean, with the geometry of the reductive monoid. So, any questions? Okay. So, an idea is that the Schwarz space should be related to some conjecture theory of pivot shifts on M rho. In particular, let me give an example. This is, again, the work of Zhilin Luo and Soclarides. In the case when f is a local function field, Then the author showed that if we take the trace of Frobenius of the conjectural intersection complex, which we call IC, M rho OF. This is conjecture. I think it's not defined yet. Then you get the basic function, something called a basic function. It's also introduced in Lay's talk. Yeah, then let's briefly review the concept of basic function. Okay. It turns out that although the whole Schwarz space is still not clear, it turns out that there should be some distinguished element in the K by K invariant subspace, which we call a basic function. Here K is a fixed maximum open compact of G. Let me see. Then there's a spectral characterization for the basic function. So spectrally, if you plug in the basic function to the zeta integral and pair it with the Zuna spherical function, then you should exactly get the standard unramified L factor for pi unramified. Okay. Here I want to mention that the zeta integral for Zuna spherical function is related to the Poincare transform, of course. In particular, the unramified component, which is exactly the Sasaki transform. And here, let me mention, in particular, one can show that the zeta integral here this is the Sasaki transform of the basic function. Evaluate at the Sasaki parameter of the representation pi s plus L over 2. Here alpha pi s plus L over 2 is the Sasaki parameter of the representation. Okay. In particular, in the standard case, then the basic function is just a characteristic function of the integer points. And geometrically, actually, you find that the Mn is smooth. So as you can imagine, that the intersection complex should be the constant sheaf. And if you take the trace of Frobenius, indeed you get a constant function on the integer points. Okay. And just like the global theory of Goma and Jacquet, the basic function plays an important role in the global theory. Okay. In particular, when you are going to form the global Schwarz space, then just like the Gluman-Jacquet case, you need to take the restricted tensor product. Then the element that you are going to take with respect to is just the basic functions. So the global Schwarz space should be the restricted tensor product over all local places of S rho. Okay. So, any questions? Yeah, this is unverified twist. Yeah, this is just pi unverified twist S plus L. So any other questions? Yeah, with respect to sigma, exactly. Yeah. So any other questions? Okay. Then we are going to talk about some basic structures for the Fourier transform. Okay. The idea of Braverman and Kazhdan is that actually the Fourier transform can be given by convolution against a G-stable distribution. Which we denoted by phi rho psi. Here, psi is an additive character of the underlying field. What is G stable mean? It just means it's a stable distribution on G. Yeah. In another sense, yeah, exactly. Yeah. Yeah. Again, let's start with the standard case. Let's first see that in standard case, we can really write down the Fourier transform as a convolution against a G-stable distribution. Then we have the embedding. And for the relation between the Haar measure on G and the Haar measure on Mn, is described as follows. Yes. Yeah. Then the standard Fourier transform is written as an integral transform on the space of matrix. Since we know that G embeds into Mn as an open dense subvariety, then we can take the integration just on the group G. And here again, the measure is the additive Hart measure on the space of matrix. Then we use the relation between the Hart measure on G and the Hart measure on Mn. We have that the integral can be written as psi trace of xy. And here's determinant of y to the nth power. Yes. dy. Here dy is a Hart measure on the group. Okay. Then in particular, we find that the integral transform can be written as follows. It's equal to determinant of x to the minus n power of gln psi trace of xy. And here's determinant of xy to the nth power and fy dy. Therefore, it's a convolution of the following form. It's determinant x to the minus n. And here's phi standard psi convoluted with f check x. And here the phi standard psi x is equal to psi of trace x and determinant of x to the nth power. So this is exactly the distribution appearing in the Fourier transform. Therefore, in order to generalize to the general case, to generalize, for general G rho, we expect that the Fourier transform f rho f should just be written as sigma g to the minus L minus 1 of phi rho psi convolute with f check g for some distribution phi rho psi here. So any questions? Yeah, I think I will stop here right now. What's phi? Oh, you mean the psi here there? It's an additive character of the underlying field. Huh? You mean general rho? It's a next talk. Yeah, next talk. Yeah. So any other questions? Yeah, on the group G, exactly. Bernstein center gives you the regular function, but this is a rational function because you will later we will show that. Yeah. Yes.